Hi, everyone, and welcome to our Power System Protection webinar series. Thanks for joining us today. My name is Josh Charent, and I'm the Marketing Manager for S&C Electric Canada. This is the first webinar of our two-part series, and it is focusing on fundamentals of power system protection, and in particular, power fuses. The second webinar in this series, which is coming up on October 28th, focuses on advanced lateral protection. It will take a closer look at applications and protection philosophies further downstream on the distribution feeder. Now, just a little housekeeping note first. There will be time for some Q&A after the presentation, so feel free to type your questions into the Q&A function at any time, and I'll read as many as we have time for at the end. We'll also send out a recording of the webinar, as well as a PDF of the presentation afterwards. In a moment, I'll introduce our speaker, but first I'd like to take a little poll to get a sense of where you're all at on this topic. So the poll question is, what is your current familiarity with distribution over current protection and coordination? Are you very familiar, somewhat familiar, or new to this topic? Okay, great. I see some responses are trickling in. I'll give it another minute or two. Okay, terrific. Thank you very much for your responses. I see that we've got a really good mix of familiarity with this topic. Looks like the majority are just somewhat familiar, which is excellent because that is, that's kind of where we're focusing on with this presentation. So I think you'll find this very useful. And now I'd like to introduce our speaker. His name is Hemanth Jala, and he's the Product Portfolio Manager in the Fuses and Circuit Switchers Product Development Group at S&C. He has over 13 years experience in the electrical industry, and he is currently responsible for the global strategy, planning, and execution throughout the product lifecycle for S&C's fuse products. Now over to you, Hemanth.
Thank you, Josh, for that wonderful introduction. Thank you, everyone, for joining today's webinar. This is about power fuses in an overall course of introduction to power system protection. As Josh mentioned, we'll have a Q&A session at the end of the presentation, so I'd ask you to hold off your questions, or at the end, when we open it up, we can have questions, and then we can address those questions. Let's start off. This is a quick agenda overview of what we're going to cover today. We're going to have a quick introduction of overcurrent protection and coordination. And we'll take a quick look of the different types of protective devices that you come across. And we'll dive a little bit deeper into fuse general features, how actual fuses work. And then we'll take a look at the fuse application factors, and we'll also touch a tad bit on the time current curve, PCCs, and we'll all tie that into a transformer protection example and see how all the application factors come into play in protecting a transformer. And then we'll open up the floor for questions. So here I've listed the overall goals of overcurrent protection and coordination. The first one is you want to prevent damage to your equipment. The second one is improving your reliability of the system. And then the third one is you want to maintain a high level of service continuity. You want to make sure as many customers as possible are on your system have power as much as possible. We'll take a look at preventing damage to equipment. These are the goals. These are the factors that affect all the goals that we just looked at. The first one is the system design. Depending on how your system is designed, it's a radial system or a loop system. It changes the way you select protective devices and how you protect your equipment. The second one is the types and location of protective devices, depending on where you put these devices and what the type of devices you're using. Those affect the goals. And then the last one is construction and maintenance practices also affect the overall goals that we just looked at. When it comes to preventing damage to equipment, we're strictly talking about preventing damage from overcurrent faults. So in the short circuit situation, you want to make sure that you protect your high value equipment like your transformers or capacitor banks or all the other equipment. You want to make sure you protect them from overcurrent faults. When it comes to overcurrent faults, you got two major types of overcurrent faults. The first one is momentary, and the second is sustained. Momentary is something that's momentary, where you have a fault that's temporary, a tree branch falls, conductors come in contact, and then the fault goes away. Or it could be Mr. Squirrel coming in contact with two conductors, and after that happens and there's no more fault, you're back in business. With a sustained fault, it's more permanent, where you have equipment failures, equipment has failed, or you have down conductors, or other things that have a longer term of outage. The way you treat the faults, depends on what type of fault it is. So if it's a momentary outage, you can, assume that the line can be energized and stay energized, and you treat it in such a way, like using reclosing, for example. For a permanent fault, you want to make sure that you understand that there'll be an extended outage, and you want to make sure that the line needs to be fixed, need to be de-energized to be fixed for taking care of the sustained fault. Here are some next few slides. We'll talk about the overcurrent protection general guidelines. The three guidelines that are listed up here are very commonly used. The first one is you want to give the faults on your system a chance to be temporary or momentary. So when a fault happens, you want to make sure that you don't want to treat it like a permanent fault all the time, but you want to treat it like a temporary fault, except when it's completely underground system. So for example, if you have a completely underground system, you know that any fault that's happening in the system is probably not a temporary fault because you don't have tree branches or animals. So you assume that for an underground system, all faults are predominantly sustained. Second one is you want to use reclosing in appropriate areas. So reclosing is basically going through a sequence of operations, use reclosers, and you want to make sure that you use reclosing in appropriate areas. What we mean by that is you want to use reclosing in residential areas and not in industrial setting where you have large machines going, you don't want to reclose into something like that. For residential areas, you can do that, and predominantly utilities would be favorable in doing that. Now, the third one, which is pretty important, you want to make sure, because you will have faults on your system, and what you want to do is you want to make sure that the outage area is as minimal as possible for sustained faults. So if you have a sustained fault where you have line conductors down, or equipment has failed, or whatever the cause may be, you want to make sure that outage area is as minimal as possible. And tying that, we come to the point of coordination, because to minimize the outage area in case of a permanent/sustained fault, you want to make sure that all your devices are properly coordinated. And basically means that the TCCs, the time current curves, which we'll take a look a little bit later, the time current curves must be selected so that devices operate in a certain sequence. And there are two, nomenclature, the definition of devices when you're looking at multiple protection devices on your system. One is called the protecting device, and the other one is protected device. Protecting device is the device that's closest to the fault, which is on the source side of the fault, which means it sees the fault first and then operates out of it. The protected device, it's the next protection device in series with this protective device. So it is helpful when you have multiple protective devices on your system and you call them by protecting device or protected device, and it changes. It kind of makes sense when you look at it from a system perspective. So here I have a typical distribution system one line. So you have a substation transformer here with a breaker, that's feeding off a 65K fuse that is, in series with a 25K fuse that is protecting a residential transformer feeding maybe 2 or 3 houses. When it comes to looking at it from this system perspective, it's easier if you call each of these devices as protected device or protecting device. And I'll show that to you when you're looking at it from a coordination perspective. When you look at, so let's focus on looking at these 2 devices, which the 25K fuse protecting this transformer and the 65K fuse in series. I plotted those 2 device curves, the TCC curves of these 2 devices. And when you look at it from the definition perspective, the 25K fuse is the protecting device and the 65K fuse is a protected device. That is, you have this 25K fuse in series with the 65K, and you have this protecting device and protected device. When you plot the curves, you will notice that there's some interaction between the 2 curves. And you'll notice that the 25K fuse length interacts with the 65K fuse at about 2400 amps. What this means is up to 2400 amps of fault current, these 2 devices are coordinated. What we mean by that is the 65K fuse will not respond to a fault that the 25K fuse will operate. So if you have a fault, let's say 2000 amps, and it happens right at the transformer where the 25K fuse is protecting, that 25K fuse will take out that fault up to a value of 2400 amps. Once the fault current is about 2400 amps, both the devices are not in coordination. So you need to make sure that you calculate the fault current at that location. And if your fault current is less than 2400 amps, you can use these 2 devices and they're properly coordinated. And when there's a fault that happens, the device will only operate which is supposed to. We move upstream a little bit, and now the 65K fuse is the protecting device, and the breaker, which is upstream, is the protected device. And you can notice that this is the 65K fuse TCC, and you got the breaker operational curve. There is no interaction between the 2, and basically you have coordination between these 2 devices up to the maximum available fault current of 8000 amps. What we mean by that is when there's a fault of any value up to 8000 amps, these devices will operate the way they're supposed to. The breaker is not going to operate for a fault that this particular fuse 65K should operate, and vice versa. The way you want to look at that is, if I go back to this one line, you want to make sure that this 65K fuse right here will take out any faults that are happening on this line. You don't want the breaker to respond to any faults up here, because if the breaker were to operate, it's going to take out a bunch of other customers and other feeders online, and you don't want that to happen. And same thing with the 65K and the 25K. You want to make sure that when there's a fault up here, only the 25K fuse operates, not the 65K, so that only the customers that are being fed by this particular transformer are out of power, and not this whole line of customers. So that's the intention of behind using TCCs and looking at coordination and making sure that the devices are properly coordinated so that the outage area when you have a permanent fault will be as minimal as possible. On this slide, what I have is some typical protective devices that you would come across on your system. The first one are the power fuses, and the second one is circuit breaker, and the third one is single phase recloser. Now you have power fuses and cutouts, which I'm not showing up here, but these are fuses and breakers and reclosers. What we are focused on today's presentation is circuit fuses. So I decided to show you the definition of a fuse. Again, a fuse is defined in the IEEE standard. I'm not going to read through the text up here. What I do want you to take away from this slide is there are 2 key things when it comes to fuses. The first one is it's a single phase device. You apply fuses per phase, and you use fuses on a single phase basis. The second one is fuses are completely self-contained. What we mean by that is the fuses have the sensing and interrupting element combined into one little package. When it comes to, like, for example, a breaker or a recloser, you have separate components. You have a sensing circuitry and a interrupting section. So sensing would sense the fault current and then send a signal. And then there's some microprocessor or something involved that would open the contacts of a vacuum bottle or, or in SF6, and it interrupts the fault current. You got two separate sections where they're interrupting the fault. In case of a fuse, they both are combined into one. You have an element that senses the fault current and interrupts the fault current. That's the key difference between the fuse and any other protected device that you can come across in your system. When it comes to high voltage fuses, there are two types of fuse technologies. The first one is expulsion fuses. The second one is a current limiting fuse. Expulsion fuses are basically when you have a fuse that uses expulsion gases. There's some interaction between the arc and a solid material, usually a solid material that generates the gases. That would interrupt the arc and stop the flow of current. With a current limiting fuse, the way it works is it introduces a high amount of electrical resistance in the path of the current flow, and that stops the flow of current and then essentially stopping the fault current from going into the system. So these are the two main technologies when it comes to high voltage fuses. We'll take a closer look at the expulsion fuses. The next one, or next main goal that we look at when it comes to overcurrent protection coordination is improving the reliability of your system. Before we go into how the system reliability is improved, we want to understand how a high voltage fuse works, and that's what we're going to go through in the next few slides. This is an overview of a process diagram that shows you how a particular fuse, a high voltage fuse, will interrupt a overcurrent fault. The first step is a overcurrent occurs, and the element that the fuse has, the element sees the fault first and it melts. And where the element was, there will be arcing. And the next step is to kind of kill the arc and stop the flow of current by extinguishing the arc and stopping the flow of current. To do that, these are the different processes. You want to lengthen, cool, deionize, and confine the arc into a small area. And you increase the dielectric strength so that the arc doesn't continue to go. And once you achieve that increased dielectric strength, it's complete deionization, and you stop the flow of current. So that's in general how a high voltage fuse works. And we'll take a closer look at a fuse that SNC makes, which is the SMU-20. SMU-20 fuse, what you see up on the screen is a cutaway of the SMU-20 fuse. It's a power fuse, and it's available from 15 kV to 38 kV. And it uses a solid material arc extinguishing medium. The way it works is you have a silver fusible element that's up here, which is under tension by a drive spring. You see this white material up here? That is your solid material that helps with the extinguishing of the arc. What happens when there's a fault current situation is this element melts, and then there is an arc between these 2 points. And then the spring is now pulling that arc into this solid material arc extinguishing medium. That arc interacts with that medium and generates some gases, which goes through that process of extinguishing the arc. And essentially, it'll stop the flow of current. And I'm going to show a sequence of operation in the next few slides on how this actually works. So this is a 90-degree rotated fuse unit. In real life, this fuse is actually 90 degrees rotated. I just put it in a horizontal position so that you can see clearly. This is a fuse in a mounting. So these are the top, that's the top, and this is the bottom of the mounting. And you got the cables coming from here, and you connect here, and then the load is connected to the terminal pad that's up here. The red path that you see on the screen is the flow of both the fault current and the load current. So at this point, what's happening is there is a fault current in the system. Fault has occurred, and the fault current is flowing through the fuse at this point. The first step that's going to happen is that element that you see up there, that has melted away, and now you have an arc between these 2 points. That is shown by this this slide. And what's happening here is, remember that spring I was talking about earlier? That spring is now expanding. You can notice that. And now this arc is being pulled into this solid material chamber. And then the arc is really hot, and what's going to happen is it interacts with the solid material, and it's going to generate some gases. And those gases aid in the interruption of this particular arc. Once that arc is being extinguished, at the end, what happens is there's no more current flowing through. And at the end, what happens is there's an arcing rod that punctures to the top of the fuse unit and disengages a latch that's on the top of the mounting, SMD20 mounting. And once it disengages the latch, the fuse unit drops open. And now you have a visible indication that this particular fuse has operated. So that in general is how a power fuse operates. You may also see fuse links and cutouts on your system. The principle of operation is still the same. You have a helically coiled, in our case, a helically coiled silver fuse element in the fuse link. And when that element melts, what happens is this cable is under tension when you install it in a fuse tube, which goes into the cutout. Once this element melts, the spring is going to pull this cable. That arc is going to interact with this particular solid material sheath for some level of current, and for higher levels of current, the fuse tube will generate the gases to interrupt the fault. The next slide shows you a little bit detail of that flipper spring. There's a flipper spring at the end of the fuse tube of the cutout, and that actually puts the tension onto the cable. It's actually pulling it, and you have a tension on the element, and when the element melts, it goes through the process we just talked about. So once this operates, what happens is the fuse tube drops open, and that's your visible indication that that particular phase has a fault, and you need to go check the fault, clear the fault, come back, either put back the new fuse unit or replace a new fuse link and close it back in, and you're back in business. When you use fuses in indoor applications, indoor would be in a piece of switchgear, like a pad mount switchgear. The main difference that you would notice is you will have a silencer or an exhaust control device at the end, because with expulsion fuses, remember, it's generating the gases, and you want to make sure that you capture anything, any gases that are coming out. Because this is inside a closed cabinet, you want to make sure you capture that. So when you have fuses in indoor pad mount switchgear applications, you'll almost anywhere you'll see a silencer or an exhaust control device, and that basically captures any gases that are being generated. You'll notice that this fuse is an SMU20 fuse, and our SMU20 fuse, you can use it in both outdoor and indoor applications. And when used in indoor application, what happens is this particular, when the fuse operates, there's an indicating pin that pops up. It's red in color. So when you open the cabinet, you'll see a red popped up indicator, and you'll know that that particular phase has a fault. So what you do is you control the line, you clear the fault, you come back, you replace the fuse unit, and you close it back in, and you're back in business. Your customers are now have power. So that's the main difference between indoor and outdoor. In indoor applications, the expulsion fuse doesn't drop out. It just provides an indication, and it has an exhaust control device. What I have up on the screen is a current limiting fuse. This is manufactured by a different manufacturer. Current limiting fuses work in a different way. The way it works is you still have an element that carries current, and when there's a fault current situation, the element, you notice there's small holes on the element. This is the silver ribbon element. What happens is at the point where you have these small holes, those are the first areas where when you have a high amount of fault current flowing through it, those are the areas where it will melt, because that's a small surface area, right? This whole thing is filled with pure silica. And what happens is once that, that element hole melts, you'll have a arc in the place where it melted. And that arc is really hot, and it's going to interact with that silica that's enclosed around the silver ribbon. And when it interacts, because of the heat generated, Silica, when you heat it up to really high temperature, there's a material called fulgurite that's formed. And that material is very good insulator. And essentially, the more of these holes melt, there's more resistance introduced in the path of the current flow. And eventually, the flow of the current will be stopped. So that's how the fault is interrupted in a current limiting fuse. A little bit different than a expulsion fuse. With an expulsion fuse, you got gases that are being generated and there's movement. In a case of a current limiting fuse, there's no movement and there's no gases being generated, but there are, a resistance that's being introduced into the fault current path. Next, we'll take a look at the different fuse application factors when it comes to choosing a fuse, and what you need to consider to pick an appropriate fuse. The first and foremost, you want to make sure that the fuse has the appropriate voltage rating. You want to make sure that the rating of the fuse is greater than or equal to the maximum system voltage that you'll apply the fuse to. Line to line for 3-phase applications and line to ground for single-phase applications. One key thing that you need to remember when it comes to voltage rating is with solid material fuses, they're not voltage critical. What we mean by that is you can use these solid material fuses at a rating that's less than their maximum rating. For example, let's say you have a 25 kV rated solid material fuse. You can energize that at 15 kV without an issue. It'll perform fine. It'll interrupt the way it's supposed to. And you can energize it at lower voltages. With a current limiting fuse, you don't have that freedom to use that because remember, when current limiting fuse operates, it produces a little bit of over voltage, and those spikes in voltages may damage the rest of the equipment on your system. So it's recommended that you use a current limiting fuse at its rating. So for example, you have a 25 kV current limiting fuse. You can only use it at 25 kV. You cannot use it at 15 kV. With a solid material fuse, there is no restriction like that. You can use it at lower voltage. The next important rating that when it comes to picking the application of a fuse is the interrupting rating. You want to make sure that the interrupting rating of that fuse that you're selecting is at least greater than what the maximum fault you would see at that location. And you would want to put some margin in there so that for future increases in load, you want to make sure you can have the fuse that can handle that high amount of fault current. So for example, let's say you calculate 8,000 amps of fault current at that location, and you find a fuse that's 12 kA interrupting rating. Sure, go ahead and use it because in the future that you don't have to change the fuse because of an increase in the fault current. So that's one thing to keep in mind. The next one, when it comes to fuses, is ampere rating and speed. Ampere rating is basically the continuous current rating, and you want to make sure that the fuse can handle the continuous current on a regular basis. And then there's, usually there's an overload. Sometimes you'll have a little bit more current flowing through, not overcurrent, not fault current, but overloads where, all of a sudden a lot more load come into play and then you're, pulling in a lot more current. You want to make sure that that fuse, what you're selecting, will not operate for these daily overloads. Speed is basically, remember the TCC that we just looked at? TCC shows the, the operational curve of a fuse for a given amount of current, the time it would take to operate. The speed is basically the slope of that curve, and you got different speeds based on different manufacturers. So you want to select the right continuous current, and you want to select the right speed to meet your application needs. The next important thing that comes into play when you're selecting a fuse is the fuse that you select. You need to make sure it can handle the inrush currents that are associated with transformers, or when hot load and cold load pickup. Hot load and cold load pickup come into play when you have reclosers on the system, and reclosers, as go through a sequence of operations where they open and close for 3 times or 4 times. So when they open and close, they're picking up that load, and depending on how much gap is between the time between picking picking the load up, you'll have some inrush on the system where there's a high amount of current flowing through the system, which is not typical continuous current, but it's a tad bit higher than your typical current. You want to make sure that that particular fuse that you're selecting can handle these inrush currents. Now, inrush currents are not like, they don't stay there for a long time, but there are, rules of thumb that you would use to make sure that a particular fuse can handle these inrush currents. When it comes to transformers, the important thing that you need to make sure is you want to make sure a fuse can handle the magnetizing inrush of the transformer. And we'll take a look at that when we use an example and see how picking a fuse and see how it can handle the magnetizing inrush of a particular transformer. These are the general guidelines when you're picking a fuse and the application factors. You want to protect the components against damaging overcurrents. That's your, remember that one goal, the first goal, protect damage against overcurrents. You want to make sure that your fuse that you select will clear the faults before it reaches a harmful level that would, basically damage your equipment. And then the second part is you want to make sure it coordinates, the fuse coordinates with the other protected devices on your system, like we looked at like the 65K and the breaker example earlier. This will ensure that you'll remove the least amount of load when there's a fault, and the rest of the circuit has normal service maintained on the rest of the circuit. We'll take a quick look at the TCCs. I know I've used the term previously, and I'm assuming you do have some level of exposure with this. TCCs, when it comes to fuses, they're defined by two curves. First curve is the minimum melt, and the second one is the total clear. Again, minimum melt is the minimum time that an overcurrent can persist before the melting of the fuse occurs. And then total clear is the total amount of time that the fuse will take to interrupt the overcurrent. These are, some of the TCCs are defined in the standards. For example, a K speed and a T speed for fuse lengths are defined in the standard. And, manufacturers make different types of TCCs, but all TCCs are to be tested and determined at, no load and at room temperature. All the manufacturers that manufacture fuses provide TCCs in various forms. TCCs, when they were originally generated, they were published on paper. So, SNC still publishes that PDF copies of TCCs, either as PDF or like a physical copy, just like you're seeing on the screen. We also provide the data points so that you can import the data points of a TCC into your own software. And you can see how you can plot the TCCs and see how it coordinates with other devices on the system. The last goal that we set out at the beginning of the webinar was to make sure that we maintain high level of service continuity. And to see how this ties into our overcurrent protection coordination, I wanted to use an example of a transformer protection and see how all the application factors and the different factors that we looked at come into play and how we can select a fuse to see how it protects a particular transformer to make sure that you have a high level of service continuity for your customers. So this is a one line that shows you the different zones that faults could occur and which device should respond to those faults. A primary side protected device, a primary side fuse on a transformer, which is this guy. You want to make sure that this fuse will operate for any faults in this region and then this region. So any faults up here, you want to make sure that this fuse senses them and operates right away, takes care of them. And then typically, if you may have a secondary side protection on your transformer secondary side. And what you want to make sure is this particular device, the primary side device, acts as a backup protection for any faults that occur in this zone. You do have backup protection here. And if something were to happen and this device didn't operate properly or whatever, you want to make sure that this particular fuse that you're selecting on the primary side of the transformer will take care of the faults and provide backup protection for faults in this zone. Another rule is to make sure that you protect each transformer individually. So you want to make sure that a single fuse protects a single transformer. You don't want to be combining 3 transformers or more and having one particular fuse protect multiple transformers. That just improves secondary fault protection, and it'll also ensure that you'll have maximum service continuity. And there's NEC limits, and you'll make sure that your ampere rating and ampere rating that you're selecting for the fuse for a particular transformer stays within those limits. And you want to make sure that the fuse that you're selecting for primary protection has meets a certain application factors. These are similar to what we just looked at previously, and this is more particular for transformers. The first thing is you should not operate for any current surges such as inrush. So if you have a magnetizing inrush, you want to make sure that the fuse doesn't operate for that. Now, magnetizing inrush occurs when you energize a transformer the first time. So you have a fuse up there and you're energizing a transformer. You don't want the fuse to operate when you're energizing a transformer. You want to make sure it stays and holds until the inrush goes away. And then the second point is you want to make sure that you can carry all anticipated loads. So you have a full load current of a transformer, but then you could load the transformer a bit more, and you can have a little bit more current flowing through the fuse, which you need to make sure that any anticipated loading, you need to make sure that that particular fuse can handle those two. The last but not the least is you want to make sure that the fuse that you're selecting will only operate when there is a fault event, when there's an overcurrent situation. You don't want that fuse on a transformer or any fuse to operate when there's no fault, which is what we define as sneak out or misoperation. It should only operate when there is a fault on the system and that fuse is called upon to operate. So what I have listed here is a summary of all the application factors that we looked at. And I have an example in the next slide that shows plots using a software that we have called Coordinate, which is available on our website. And you can plot the various transformer curves, fuse curves, other manufacturer device curves, and see how they coordinate and make your decision using the TCCs that are in the system. This is a quick summary of what we looked at and how you would use these application factors to pick a particular fuse. First thing, like I said, you need to make sure that the voltage and interrupting ratings are appropriately selected. You want to select the ampere rating and speed of that fuse. Typically, what you would want to do is when it comes to transformer protection, you calculate the full load current value of the transformer. Then you pick a fuse that's closest to 1.3 times the full load current value. The next one is you need to make sure that the inrush currents, we're only looking at the magnetizing inrush here. You want to make sure that that particular fuse can handle any potential magnetizing inrush. There's general rules of thumb that industry has used in the past, which has been validated by testing. The one point that we've always seen commonly used is 12 times the full load current at 0.1 second and 25 times full load current at 0.01 second. So it'll be evident when we look at the TCC and the plot in the next slide. But what those two show up as is points on the TCC plot, and you want to make sure that your fuse doesn't operate for those 2 points. And again, I'm listing the design objectives of picking a fuse. What you want to do is you want to protect the transformer against any damaging overcurrents, and you want to make sure that you coordinate with the primary and secondary side devices. And you also want to protect the load side conductors and any cables that are on the system from any damaging overcurrents. Talked a little bit about transformer and how to protect the transformer. Now, you need to see how the fuse that you're selecting, how it protects the transformer and how well it protects the transformer. The way you do that is by using measuring it against the transformer through fault protection curves. Those curves are found in the standards, and I list the standards up there. And manufacturers will also provide the transformer damage curves and software that is available for free, such as, SNC's Coordinate also has the transformer damage curves. And, you got software that you can purchase that also has the transformer damage curves. What you want to do is you want to select a particular transformer and you select a fuse based on, the application factors that you looked at. And you make a decision on which fuse to use based on how well it protects the transformer and how well it fits into handling the transformer inrush and any other continuous current. So for that, I'd like to use an example, which is up on this page. So what this is what you're looking at is the output of the software that we have, Coordinate. And with Coordinate, you can select multiple fuses, not only SNC, but other manufacturers too. And you can see, you can also select the transformer damage curves and plot them and visually see how well your particular fuse that you're selecting would be protecting the transformer. So what I have here is a transformer damage curve, which is this blue line. The transformer damage curve of a 1000 kVA transformer at 1247 system voltage. And what I have done is I have plotted two curves, a 50 amp SME20, the power fuse that we looked at earlier, and then a 65 amp standard speed SME20. And what Coordinate does is it gives you the multiple inrush points as dots, as points on the curve. So remember the 12 times full-time current at 0.1 second, that is this point. And then 25 times the full load current of the transformer, that's this point. So when it comes to seeing how well a particular fuse is protecting a transformer, you want to plot the transformer damage curve, which is this guy. And the first rule is you want to make sure that the fuse is to the left of what we call the NC point. The NC point is the maximum available fault that can happen at that particular location. It's a bolted fault where you have the secondary side, bolted to the ground and you have a fault. That's the maximum amount of current, fault current that can happen. What you absolutely want to make sure is to have that fuse to the left of this NC point. And the next point is you want to make sure that the fuse that you're selecting is able to handle any anticipated continuous overloads. So for that, remember I talked about 1.3 times the full load current in taking the fuse. So I did the calculation for a 1000 kVA transformer at 1247, continuous current is 46 amps and 46 times 1.3, the closest fuse is 60, I believe 65. So what I did was I selected a 50 amp fuse and a 65 amp fuse. Next, when you want to make sure that it does handle the inrush currents properly, you want to plot the inrush points, and these two are the magnetizing inrush points. So this is your 12 times 0.1 and 25 times 0.1. You want to make sure that the fuse, whatever fuse you're selecting, is to the right of these two inrush points, which basically means that this point, if this inrush were to occur, for example, a inrush current of this magnitude for 0.1 second, you want to make sure that this doesn't operate that fuse. So you want to make sure that point is to the left of the fuse operate minimum melt current. So from this example, if I'm only concerned with magnetizing inrush, I would pick either the 50 or 25, 50 amp or 65 amp fuse, but it depends on how your system is designed and how your general rules of thumb are in your organization. Sometimes I've heard where you don't want any interaction between the operational curve, which is the damage curve of the transformer, with the operational curve, the TCC of your fuse. So if that were the case, this is intersecting with the transformer damage curve up here, the 65E, and the 50E is not intersecting at all. But you got to keep in mind a 50 amp, the 50 amp fuse is only a little bit more than the full load continuous current, which is 46 amps. So you have to make a decision. Would I go with a 50 amp fuse or a 65 amp fuse in this case, even though it intersects at a very low point on the transformer damage curve? That's the other rule. You want to make sure that your fuse you're selecting interacts with the transformer damage curve at the lowest current possible. So ideally, no interaction. But if it does interact, you want to make sure that it interacts at the lowest current possible. That way you get full protection on the transformer. So that's how all this ties into together. And visually, this is how it'll look. Again, this is based on Coordinate software that we have used. Depending on what software you're using, it may be a tad bit different, but the process of selecting a fuse and looking at the mesh points and making sure it protects against damaging currents is pretty much the same. So that's the example I wanted to show. And with that, I have completed the slides, and I think we can open up the floor for the questions. I'm going to open up the floor for the questions, and I'm going to hand it over to Josh.
Thank you, Hemanth. Great presentation. So we have a few minutes for some questions, and just to remind everybody, if you want to ask a question, there's the Q&A function in the toolbar at the bottom. You can feel free to type in a question there. So Hemanth, the first question that I've got here is, for what applications is an expulsion fuse better, and when is it better to use a current limiting fuse?
So very good question. First, there's differences between the operation, right? So depending on your needs, the one thing that I would mention is with a current limiting fuse, you do get a much higher interrupting rating. So if your interrupting rating is, for example, current limiting fuses can go up to like 50 kA fault current interruption. But at the same time, current limiting fuses get heavier with high continuous current. And there's handling issues, and also it comes to the point of you can only apply it at that particular voltage, right? So you need to make it take into account your system and which one would benefit, and you want to use for example, for protecting your transformers, cutouts and power fuses have been used for a long time. And it provides a very good way of protecting the transformer and also coordinating with another device. So depending on your particular system, I would say, look at what you want to pick, and then you can choose an expulsion fuse or a current limiting fuse.
So another question here is, what were the other points at 1 second, 10 seconds, 1,000 seconds on the last plot shown with 2 fuses protecting the transformers? Are these the cold load pickup? If it is cold load pickup, isn't 65 amp better than 50 amp fuse?
Exactly. You basically answered the question in your question. So those are the hot load and cold load pickup. So again, it comes to the point of if you have cold load pickup, or if you're concerned with cold load and hot load pickup, you would pick a 65 fuse in that particular case. If you're only concerned with magnetizing inrush, you could go with either the 50 or the 65.
Great. How do you determine the full load current for the transformer?
So, it's basically calculation. You could use software, or you could do calculation. So 1,000 kVA at 1247 is 1,000 divided by 1247, and then you divide the result with 1.732 because there's a single phase, right? So you get to the 1,000 divided by 12.47 is about, I think I did the calculation, about 80 amps, and then divide that with 1.732 square root of 3, you get the single phase current, and that's what you would use. So.
Cool. Next question is, if I have surge arresters at the fuse tap off on the power line, would it be better to install the surge arrestor above or below the fuse?
So depending on, predominantly, what you ideally want to do is, let's say it's a transformer, I'm assuming it's a transformer protection. you want to make sure that the surge arrestor is on the transformer tank to provide full surge protection on the transformer, right? But at the same time, if you do that, now your fuse or whatever fuse, most of the time it's a cutout or a power fuse, that is now exposed to surges, lightning surges, right? So if your fuse or fuse cutout is going to operate for those lightning surges, you may want to think about using the surge arrestor in front of it. But if your fuse cutout or the fuse that you're using is designed such that it can handle a high amount of surge, then you can put you can put the surge arrestor on the transformer tank, and then put the fuse in front of it because it can handle the surges, lightning surges much better. So it depends on the design of the fuse. And that's how you would make the decision.
Okay. Next question is, what is the difference between a K and E type fuse?
So remember I was talking about the TCCs being defined in the standard. So in the standard 3742, there have been two fuse links that have been defined, a K speed and a T speed. These are for the fuse links, the stuff that goes into the fuse tube and into the fuse cutout. What SNC has done is, based on customers' feedback, we've been requested to create a power fuse curve that emulates the K speed of a fuse link. So our SMU20 K speed emulates the fuse link's K speed. Well, the E rating is basically, there are 2 points that you need to meet, and that's defined in the standard. And as long as you meet those 2 points, you have an E-rated fuse. So it's basically a different type of fuse. The TCCs are a little bit different, but the origins, again, like I said, comes from what's in the standard.
Okay, great. So I think we have time for just one last question. The question is, can you confirm that the power fuse is designed to continuously carry 150% of their continuous rating? If yes, would the 150% of rating loading have a duration limit in hours, days, or months?
All right. So I want to make sure I explain this and make sure that it's properly understood. So you have a fuse that's rated 50 amps, right? And when you look at the TCC of a 50 amp fuse, you'll notice that it'll start to melt at like about twice its rating, about 100 amps. That does not mean that you can load like 90 amps through that fuse. No, the fuse is still rated 50 amps, okay? But every manufacturer, including SNC, we publish the overload / peak load capabilities of a particular fuse. So, and we publish in documents, for example, for SMU20s, the document would be 242-190, and it'll tell you for a particular fuse how much more current it can handle. So a 50 amp fuse can handle up to maybe, I think, 60 or 65. I don't know if I remember off the top of my head, but it does have a little bit of overload rating. You cannot assume that there's a rule of thumb like, oh, 150% I can load this. No, it depends on what the fuse can handle. And we do publish continuous overload rating and like 1 hour, 4 hour, and 8 hour overload rating. So we publish that, and you need to make sure that you're not putting too much current or more current than what it's published. So we do publish that, and depending on your device that you're using, you can figure out which fuse can handle how much current.
Okay, great. Thank you very much, Hemanth.
Sure.
And that's all the time we have for today. Thank you all very much for joining us, and I hope you found this webinar valuable. Have a great day.
All right. Thank you, Josh.
Thanks.
Thank you, everyone.